4. Hello and welcome to Digital Futures tutorial. Today we have a very exciting tutorial and a most awaited tutorial on robotic fabrication. And we have Ethan Kerber from Germany joining us today. He is also one of the important person working with robots in architecture. For those who are aware about the amazing work that is produced by KUKA-CRC. Ethan, we are really, really happy to and glad to have you here today. Before we jump on to today's session, let me just quickly make some announcements for our upcoming session. Today in the afternoon at 2 p.m. EST, we also have our second in series of tutorials on AI and prompt engineering with Midjourney, DALL-E. This is a series that has 8 tutorials, and today will be the 3rd tutorial, which will be an introduction to AI for designers. Please join us if you're interested in this session. Also, tomorrow we are starting with our series of architecture and philosophy sessions, which are part of FIU's DDES doctoral consortium. And we'll have our first session tomorrow on at 10 a.m. EDT. And now on to this tutorial. So I think there is a lot of learning in this tutorial that's going to come through, and I'm really excited about this. But let me just say a few words about Ethan, and you will get to know him a little bit more today. Ethan Kerber is a computational designer working at the intersection of architecture, engineering, and construction. He has experience in metalwork and digital fabrication with public sculptures permanently installed in Washington, D.C. and Arlington, Virginia. Ethan is the CEO of Robots in Architecture Research, managing editor of the Journal on Construction Robotics, and a researcher at the Chair of Individualized Production, where he is developing a doctoral dissertation on automation in steel construction. Welcome to Digital Futures, Ethan. This was a long-awaited tutorial, and the screen is all yours.
Thank you so much. It's a great honor to be here. It's a great honor to invite you digitally into the world of Aachen, Germany, where we have a lot going on, a lot of interesting research. As you heard from my introduction, I'm quite a busy little bee. I've got a lot of irons in the fire, from my doctoral dissertation to my work in robots and architecture research to my work on the Journal of Construction Robotics. It's just a real pleasure to bring you this tutorial on cloud remote control. And I wanted to start off with just a brief introduction about the process and what we're going to be doing, and then do some demonstration of it, and then try to move on to actually let you try to work with the plugin. So we'll talk for about 30 to 40 minutes about how this plugin came about, what we're doing with it, what it enables, and then we will take a coffee break and do some installation for those of you that are on the Zoom live with us today. And we will try to walk through some of the demo file that I've prepared for today and let you control the robot remotely yourself. So hopefully that'll be fun. I've done a lot of cloud remote control demos throughout the course of the last 3 years, and they've all gone well. So today I'm really excited to share this experience with you. If you have any questions, I come from the type of family that talks and talks and talks until we're interrupted. So please feel free to raise your hand or turn on your mic or speak up or put something in the chat. Otherwise, I will just ramble on, I promise you. Let me go ahead and share my screen. Great. So some information from the lawyers. This is generally for educational purpose. Cloud remote control is still in beta. It's not yet available to the public. We're doing select demos and trials and iterations on it. But if you're interested after this tutorial, and maybe you're watching this after the live tutorial is come and gone, and you want to try this for yourself, please feel free to contact me. I'll talk about my email and how you can get in touch with me, but you can always hit me up on LinkedIn, certainly under Ethan Kerber. I have the distinct honor and benefit of working with and for the Professor Sigrid Burrell-Chochan at the Chair for Individualized Production, and in collaboration with the chair and the RWTH Aachen, I am realizing my dreams of collaborating closely in metalworking processes with all sorts of interesting robots. And so here you can see me and two of my good mobile collaborative robotic friends teaching each other how to weld and pick and place rebar. Professor Burrell-Chochan is amazing and well connected in the world of robotics. She has a long history from founding the Association for Robots and Architecture to starting the Chair for Individualized Production, from working at the EU Construction Robotics journal, and then being a previously on the board of directors at EU Robotics. Myself, I am lucky to be here and working with the amazing international team that she has been built, and to be given the honor of taking a leadership role in the commercial side of robots and architecture. The Association for Robots and Architecture was started by Professor Burrell-Chochan and Johannes Brauman almost 10 years ago, and was one of the earlier innovators in bringing robots to the creative industry in a really accessible way, on the edge of kind of the popularization of parametric modeling. They built this plugin KUKA-CRC that allowed for people to mass customize robot programs. And from that, there was such excitement about this increased accessibility, this new ability to play with digital fabrication and digital craftsmanship, that the association started a conference, which I hope many of you have been to. And if not, I hope you do come to them in the future. During our conference, we publish a book on robots and architecture. We also, from that, have spun off a journal on construction robotics. After 10 years of seeing robotics being more accessible to the creative industry, we still have not yet seen the flood pour over into robots on construction sites. We see that starting, and we want to be a part of that key movement. And so the Journal on Construction Robotics is a central location where you can read about and hopefully publish your work in taking robotics outside of the lab and the prototype environment, and really impacting change in our industry, which is in desperate need of innovation and digitalization. I hope you can hear this. It's a little too loud. And part of what we do at the Association for Robots and Architecture and Robots and Architecture Research, the commercial side of the association, is we host the Robots Conference. We're really excited that we're about to announce our next Robots Conference. This is a great video from our previous Robots Conference, which was at I believe it's 2018 already, so long ago. We meant to have one in 2020, but as you know, the world kind of put on their pajamas and stayed home for a few years. So we're really excited to bring the community back together again and play and party and celebrate and innovate and discuss what we've all been doing in the meantime throughout this strange stretch of time. The Robots Conference is well known for bringing together industry experts in robotics to test and demonstrate some really interesting processes with robots, to do workshops, to do demos, to do lectures, to celebrate achievements, to eat, to network, to build kind of community, to push the industry and the innovation forward. I took at the last conference a really interesting workshop by Foster & Partners, which was focused on spatial 3D printing, and it really inspired me to get deeper and deeper into all sorts of types of robots. As I said, we're really excited to announce soon Robots 2024. I can't say anything about it yet, but we really hope that you'll all join us together to gather and celebrate and build our path to the future. Okay, so what are we here to do today? Well, during the past 3 years,
Acadia 2020.
Let me pause this. During the past 3 years, we miss you. Definitely, we miss you. We miss traveling around the world. We miss going to teach workshops in international locations, and we really wanted to continue teaching throughout the pandemic. So we started to build something called Cloud Remote Control. We took all the advantages of KUKA-CRC, of parametric robot control, the ability to move robots through Rhino and Grasshopper, and we brought it to the cloud. We brought online collaboration to digital fabrication. So now from anywhere in the world, people can log on and control and monitor the processes of robots using the next generation of KUKA-CRC edition called KUKA-CRC, Cloud Remote Control. This has been great. We've had people from 17 different countries control robots in 2 different countries at once. And today I want to know certainly where you are from all around the world watching and hopefully participating. So maybe in the chat, you can put where you're at in the world. I think this is going to be a really international audience, and I love that. Part of my goal in my research is to bring the world's robots online so that you can be on a beach in Bali and still fabricating in a facility somewhere in Europe. You can be on a mountaintop in Switzerland and still be, you know, welding with robots in some place in Colorado. You can be working in your office in New York and still fabricating in a facility somewhere in South America. I really love this idea of distributed collaboration. I think the whole world has gone to a new level of comfort with Zoom meetings, and why shouldn't you be able to control a giant plasma cutting robot during your Zoom meeting? I know in my Monday morning, that would make my Zoom meeting a lot better. Okay, so through parametric control and cloud remote control, we can create mass customized design to fabrication programs that allow us to simulate, to animate, to create mass customizable robot processes that can generate robot code directly from design models. So we get all the benefit of early design decision assistance tools so that we can make our designs more buildable with robotic processes. We have to take constraints of robotics, of which there are plenty, and turn them into characteristics of our designs. And if we can, at the earliest stages of parametric modeling and our design processes, consider not just structure and sustainability, but also digital fabrication, we can start to bring down the cost of complexity in construction through the power of computational design, optimization, engineering, and also digital fabrication. I really love this idea because I've worked in industry and we've always had very amazing ideas, and sometimes they hit the wall of being too expensive to fabricate because all the designs are mass customized. Rhino, Grasshopper, Dynamo, C#, these powerful programming tools all give us the ability to design and engineer very complex, highly optimized structures. But if we can't build them effectively and efficiently, then sometimes they don't get realized, or at least they're not cost effective to realize. So what we'd like to do is bring robotics very early to the design decision process so that we can understand, okay, 80% of my design is fabricable by robots. Maybe if I need a bigger robot, I have to go to a bigger facility, and maybe I can log into that facility with cloud remote control and start pushing code to it. What's interesting about cloud remote control is it also extends a lot of this access to robotics, not just to you online around the world, but to robots working with each other, robots working with different devices. There's a whole IoT-enabled infrastructure that underlies the concept of cloud remote control that allows us to much more easily connect end effectors to the robots. Because we're going through the cloud, we no longer have to have the grippers connected to the ins and outs of the robots. We're communicating through an IoT-enabled MQTT network so that I can have this robot interacting with many, many different tools as long as they subscribe and publish to this KUKA Cloud Remote Control protocol. So while online access is interesting educationally, certainly IoT-enabled robotic processes that enable digital twins and dynamic adaptivity is much more interesting from an industrial point of view, where you might not want somebody from around the world controlling your robot, but you do want to make a much more intelligent, complex, connected robotic process. I feel like I'm rambling and you're all like, where are the robots? Bring me the robots. So without further ado, we should probably get to the robots. And I'll come back to this presentation, I'm sure, a little bit later. Let me jump to Rhino and Grasshopper. For a second. Great. So let me just look real quickly at the chat and see. We've got people from Chile, from Miami, from Indonesia. Awesome. All over the world. I've been to Miami, I've been to Chile, never been to Indonesia. I'll have to get on a plane. That sounds great. I'm from New York, actually, originally, but working here at in Aachen, Germany. Okay, let's jump to Rhino and Grasshopper. So I wonder how many of you have familiarity with Rhino and Grasshopper. Maybe you can put that in the chat as well so that I can get a sense of how quickly we can dive through these things. Okay, 1 second. Great. So I think we're all, I've got an intermediate user. I hope you're familiar with Rhino and Grasshopper. If not, there's plenty of really interesting courses, I'm sure, including some by DigitalFUTURES. I know the Chair for Individualized Production has some great courses online. We're actually preparing a massive open online course that we hope to share with the world soon about Intro to Robotics. I want to walk you through a little bit about the process of how to work with robotics. The first thing is that, let me explain that everything we're doing here with cloud remote control is an extension of parametric robot control. So if you're learning the philosophy of how to move robots today, forward kinematics, inverse kinematics, axis movements, interpolation, all of this can be done with KUKA-CRC without connecting to the cloud. KUKA-CRC is a well-known plugin for parametric robot control that's been used by over 100 academic institutions around the world and many, many industrial institutions, of which I'm proud to partner. And it's really amazing. It's my one, I mean, I've got every plugin that is on Food for Rhino. I collect them like baseball cards, in KUKA-CRC, one of my favorites. It allows us to mass customize robotic programs and build really amazing things. Now, compared to something like SolidCAM or a milling specific program, KUKA-CRC is more a set of tools where you could design your own robotic processes. So if you want to put a spray can on the end of a robot and do some painting, or if you want to put a mill on the end and do some milling, or a welder, a plasma cutter, or a 3D printer, or another robot arm, you can do this with KUKA-CRC. It's made for creative people to get access to the digital fabrication process and develop it themselves. Now, robots are pretty agnostic. They really don't have anything on them by default. This is my little toy robot here. And so you can put whatever you want on the end of it. And KUKA-CRC allows you to design custom tools to enable you to work with devices that you might have made yourself in a shop with your 3D printer and your imagination. A hot wire foam cutter, I don't know. The things I've seen put on robots are endless. I recommend you not put yourself on the robot. That's not a good idea. Try to put some tool and you stay at a safe distance. Okay, so the first thing that you should know is working with robots boils down to two major types of motion. There's forward kinematics, where you're moving the robot axis by axis, telling the robot very specifically, move joint 1, 10 degrees, joint 2, 20 degrees, so on and so forth. And then there's forward kinematics, where you're telling the robot, take the tool center point, the TCP at the edge of the flange right there, and move that to a specific plane in space. You need to move it to a plane because it's not enough to move a robot to a point, because a point is just X, Y, and Z, whereas a plane is X, Y, Z, A, B, C. So if a robot's moving here, that's X, Y, Z, but here is the same X, Y, Z, but with a different A, B, C. So it really comes down to working with planes. If you can create planes, then you could push a robot through those planes and do a lot of interesting things with it. So I want to get started first off talking about cloud remote control and how you can connect to the server online. So the first thing that we want to do is bring down this little core component, which got a lock on it, and set this to your specific username and password. For those of you participating live today, I've set up username and passwords based on your email address. For those of you who want to try KUKA-CRC later on, shoot me an email, ethan@robotsandarchitecture.com, and we're going to be setting up some more workshops in the future. We'd love to have you participate if you're watching this later. Okay, so once you have this logon and connected, you can toggle this to true. You also do have to set the address. If you go to set login, you can see that this is the address right here that you would copy and paste into a second to move things out of the way. Copy and paste into a panel like so, and then connect that to there. We're making KUKA-CRC extendable so that other institutions can deploy this in the future on servers of their own. And then once you log in, I got nervous there for a second, you do get this connected and login successful. What's happening with KUKA-CRC is that you're allowed to register with the system and then push commands through the cloud to our local server. And if you're authenticated, if you've got if you've registered successfully and got the credentials to use our robots, because safety of our robots through remote channels is our highest concern, then you're able to push code to the robot. You're able to stream from your computer around the world to our cloud server, to our local server, where it's distributed throughout our IoT-enabled devices. What happens at that point is that the robot is then communicating state and process information back to the cloud, back to your computer, so you can monitor a digital twin of the real process live. This is really interesting, and in my own research for PhD, allows us to do all sorts of interesting things with this digital twin data, like including updating metadata and starting to build more dynamic state-based processes. So now, though, we're really using it to push digital twin information. So once we're logged in, what we want to do is make our first movement. In order to do this, we are going to set up an axis movement. We're going to send these movements to a simulation of the robot. And then as we move our simulation slider, we'll see the simulated robot enact our program. Now, in this case, we're going to be using an axis movement from KUKA-CRC. Keep in mind that these axis movements are also available in KUKA-PRC. So if you only have PRC, because KUKA-CRC is not yet available, I'm working hard to make that happen, then you can do these same things in KUKA-PRC. Okay, so we get an axis movement, and then we create 6 different values ranging from, in my case, -100 to 100. Copy and paste this 6 times, merge this together, and push this into the axis value. Now, KUKA-CRC is designed for enabling multi-robotic factories. So we also have to tell KUKA-CRC which specific robot we want to send these commands to. In this case, you can see my lovely assistant here, Optimus. That's our prime robot. And we're going to send these commands all to Optimus. Once we have those commands set up, I like to keep a little data component here that's called toRobot. Now, in a longer workshop, I would build this whole model with you from scratch. And maybe after we get the plugin installed, we will go through this. But as a tutorial for those who are watching this later online, I want to go through the concepts before we get into the nitty-gritty details. Once we have our data coming through a data component called toRobot, which is just data, let me actually set up bifocals, which maybe helps people that don't appreciate that I'm using icons and not full names. The bifocals is a little plugin that just displays more information about the plugin. You can see what these things are if you're watching this live. What we're going to do in order to leverage the simulation process from KUKA-PRC, is we're going to take these KUKA-CRC commands, translate them into PRC commands, and use the PRC core to simulate them. In the future, we are going to build a core inside KUKA-PRC, inside KUKA-CRC that does simulation as well. But for now, it's all one family, so we're leveraging the tools that we already have. We need to tell KUKA-PRC what type of robot we have. Now, KUKA-PRC does support a wide range of all the KUKA robots that I've experienced, and we're certainly adding more as they come available, but KUKA-PRC does focus on KUKA robots. We also need to tell it what the geometry of our tool is. In this case, you can see I have a shunt gripper on my robot, and I've set that to these calibration values according to the 4-point calibration that I've gone through manually with the robot. But if you have another tool that you want to put on your robot, for instance, a simulated tool like a spindle or a custom tool that you're planning on creating and putting the robot in your lab or garage or office, you can certainly do that through custom tool commands as well. KUKA-PRC offers a lot of accessibility and deep functionality. You can look at the advanced tab to find out more and more information about start and end positions. I like to set my initial posture as start. I like to set these values as my start position because that's what's tied to CRC as a home position. And I like to put alt after last program position so that when I move my simulation slider to the value of 1, it's showing me the last position. You can also find on here the analysis tab, where if you zoom out, you can see the axes of your robot. Right now, it's just a axis movement. So this is the most boring analysis graph I've ever seen. But as we get into more interesting adventures, this should get a little wilder and show us the axis movements. You can also in here do collision checking and turn on output analysis values if you're looking to integrate things like Galapagos or Octopus, which are evolutionary optimization tools in your robotic process. So if you're not sure where on the table you can reach something and you want to have your parametric model optimized computationally, you can output analysis values and set Galapagos to work figuring out where's the most reachable position for the object you're trying to assemble or mill or something. Okay. So once we have our robot set up with our simulation, we can look at what that robot commands are going to look like. In my case, I see that I have one thing that I'd like to turn back on, which is show toolpath. And now you can see that toolpath here. Now this is quite a boring little program, just an initial axis movement, but let's try to push it to the robot. Now, in order to push this to the robot, we're going through the same robot commands, but we're going to use the KUKA-CRC core component to book the robot and send it to the robot. Now, I happen to be already booked because I was testing this from before, but I'm going to do one last thing before I send it. Using the live robot display component, which can be found up here, display KUKA-CRC, I'm going to tell Cloud Remote Control that I want to monitor this device. I want to turn the 3D model to true, and I want to use a trigger, which is going to tell this component how often to update the live preview of the robot. What this is doing is this is pulling information from the real robot process and simulating it as a digital twin. I generally like to make this light gray just so I can see the difference. But if you turn this on, you can see also that this does come in with the colors of the KUKA robot. Nevertheless, everyone's got their personal preference. I like it light gray. Good. KUKA-CRC offers accessibility to users around the world. It also offers local operators override control. So if you're moving the robot, I can be sure to slow it down, to pause it, to stop it, to cancel it, to approve access, and to securely have local control over the robot. So please don't worry that you're going to do something crazy with the robot and it's going to run wild. We're here controlling it, making sure that it's running at a safe speed. And if we see something not going right or well, we can pause it and stop it and adapt it. This is a great blend of distributed automation and local control. Let's see. So let's go ahead and send this to the robot by switching this to false and true. And you can see that the robot went to it. Why this didn't update? That's a great question. We'll get to that in a second. Let me turn that back off. I think in this case, I'll have to restart my Rhino and Grass. Would. Okay. But access values are pretty difficult to use. Say I wanted you to pick up a pen with forward kinematics, you'd be here all day trying to move this to 1 and figuring out exactly where these values should go to pick up one specific item. So what we can do instead is focus on inverse kinematics. This is forward kinematics. And now let's set up some inverse kinematics. In inverse kinematics, we're going to take a point right here, in the case of my Rhino model. We're going to create a plane from that point, in this case, an XY plane. And we're going to use that plane in order to push the robot through a limb movement. Move some things around. Add some wires here. So what we're doing is taking our plane, pushing it through a KUKA-CRC limb movement, and then we can merge that command with our axis movement. So the first thing I want to do in my robot program is this axis movement, and then this limb movement, and then return to that axis movement. So once we get this set up, Let me stop sharing my screen one more second so I could get rid of this little artifact from this Control Alt. Second. Let me go ahead and restart my Rhino and Grasshopper just to give a fresh start to this because I still seem to have this artifact stuck here. Actually strange to go through this as a tutorial. Normally I go through it much more with people. I'm not sure if I'm doing a good job, but I hope so. Let me just restart Rhino and Grasshopper.
Yeah, maybe I can jump in and see if anyone has any questions. Do you, Ethan, if there are any things that, any downloadable links that students can start to download while you wait?
This is a great idea. Let me
Yeah.
just restart Rhino and Grasshopper and I'll share that with you. Okay. So what I'd like to do, it's actually 4:35 already. What I'd like to do is just show one more movement and then take a moment to share the link. We'll take maybe a 10 or 15-minute coffee break to turn off the live stream and we'll get it installed. And then we'll build from scratch some of what I'm showing you today. Because I know it's really hard to look at some spaghetti and think, wow, I know what the heck this guy's talking about and I could recreate it myself. It's always best if you start from a blank canvas and we build it up step by step. But for those later who are joining, I wanted to walk through it a little bit conceptually so that if they don't have access to the plugin, they can still see the process and get excited to contact us. Let me go ahead and share my screen one more time and we'll go through one more slightly more interesting motion. Okay, so we've got but everything with robots, at least how I work with robots, largely comes down to planes. If you can generate planes, it's very easy to start to create robotic processes. So from this axis movement, we want to move the robot to this point, but not just the point, to a plane. So we're taking this point, we're going to make this XY plane and push this plane to a limb movement with the robot. Once we have that set up, we can check that this is not bright red. If it's red, it's going to say, ooh, reachability or collision. We can run the simulation slider, see if that looks good, keeping an eye out for singularities or collisions or reachability issues. And let's see if this is working. We can push this to the robot. There you go. Now our digital twin's working nicely. And you should see there's a window in the Zoom where you can see the robot actually moving. Now I'm sure you're thinking, well, that's fun for you, Ethan, but I want to try. I want to move the robot. These are the two most simplest demos that I have, which is one, pushing an axis movement, and two, pushing a more inverse kinematic motion. But I've got some other examples set up that I want to share with you. But I think what we should do is take a 10-minute break. Let me get the plugin installed for some of the people that are collaborating with me online live today. And then we'll walk through from scratch how we can set up some of these files. So I think let me stop the share and we'll go ahead and set this up because I think that's a more engaging experience for people rather than seeing me play with the robot is to give the chance for people around the world to play.
Sure. I think most of people joining us today, we also have a question. I don't know, Louis, would you like me to ask the question for you?
I could see this question.
Yeah, okay. Yeah. Does it require MX automation or KUKA or proxy or it's a custom KUKA?
It does require KUKA MX automation. I want to say this as well. KUKA-CRC right now is built for the latest build of Rhino and Grasshopper and for PCs. So I apologize if you're a Mac user, we've not yet extended that to that ecosystem. I'm sure anyone calling from San Francisco is hating me right now. I apologize. Most of the mechanical engineering world and the robot world, I think, have PCs at their fingertips. So let me go ahead and share the SIBO link with the group. Maybe we take a minute to pause the live stream.
We won't be pausing the live stream, but we can take the time to interact and work. Yeah.
Great. Maybe before we do that, I'd love to hear from people, to see some people's faces, and to maybe introduce yourselves so that I have a sense of who we're working with. And so normally what I do to start these workshops is I say, hi, my name is Ethan Kerber. I'm from New York, but I'm in Aachen, Germany. One of the things I love about cloud remote control is bringing together this online global community. So I'd love to hear from you, how to pronounce your name so I don't mispronounce it, and where you're from in the world.
Mm-hmm. So I think, yeah, we can start if people are comfortable with switching on their videos, or if you're not, just unmute yourself and say. I see Leandra is there, if I'm not pronouncing the name wrong.
Yeah, hi. So maybe I just start then. I'm from Germany, Berlin, and I am interested in digital fabrication in general. So I was working with these small robots, universal robots, these cobots. I was like programming a bit with Grasshopper, doing some movements, trying out different end effectors. Like I had this industrial gripper where I could grip fabric by freezing. And yeah, I did really basic movements, but also I did wood milling a bit with a robot in a project. And my background is product design. So I'm really curious how to design for digital fabrication, even though I'm not like super high elaborated in this programming and technical stuff. But for me, I was writing my bachelor thesis last semester about exactly this problematic. So how can I somehow also provide a design or a production which is like in a distributed production system, possible like to send it somewhere else. And yeah, I was just curious, and I have a Mac. I don't know if it's like problem now.
You have boot camp?
Sorry, no.
You have boot camp? I apologize. My experience hasn't been that it functions with Mac. This is supported beta software. Even KUKA-CRC actually is just now being extended to the Mac ecosystem. So I apologize.
Okay, I see. Maybe I'll just follow.
Yeah. I put a link to a SIBO on the chat here. You can download this. This comes with a very temporary license. There's a couple of things to make the installation successful. One is that you should download this zip file. Let me actually go to that SIBO and share it and look at that myself. So you should download this zip file and absolutely make sure that you unblock it before unzipping it. Otherwise, your computer will see it as malware. Also, please note, if you have an existing installation of KUKA-CRC, please take that out of your libraries folder and put that onto your desktop or someplace safe for installation later. The plugin I'm giving you includes a version of KUKA-CRC as well as KUKA-CRC. So once you've got that downloaded, right-click on the zip file, go to Properties, go to Unblock, and then unzip it into your libraries folder for Grasshopper. If you're not familiar how to get to your libraries folders from Grasshopper, I can certainly point that out. You can go to File, Special Folders, Components Folders, and this is where you should put the unzip, the unblock, unzip plugin. And with that, then you'll get to have the KUKA-CRC toolbar as well as the KUKA-CRC toolbar. I've also given in that SIBO file a link to a text file that explains everything I just said, as well as this demo file right here that we can walk through. But I would prefer that we start from scratch and build it up a bit together. Let me actually do, yeah, that sounds good. Ali, where are you from? Oh, we can't hear you.
We can't hear you. You're on mute.
Hello again. I'm from Iran, but currently I'm in Barcelona. I'm working at IAC, 3D printing department. So we are printing by using KUKA and other devices. I have also a Mac, but Johan was so kind to send me a link about 6 months ago. I installed the KUKA-CRC for Mac. It's working. I think it's the temporary version that you mentioned. And yes, that's about me.
Yeah. Is there somebody here, let's ask, that's on a PC that we can get it? Louis, so you happen to be on a PC? Great. Tell us a little bit about you. Where are you from?
Well, let me read someone else.
DJ Luis.
I'm originally from Mexico, but currently I'm in Miami actually with Bablin. So we have PC. I have used KUKA-CRC for some years now, but I haven't tried yet CRC. So I'm excited.
Great. Let's see. Can you download that from that link I sent you, and let's try to get it installed for you?
Yes, I am.
Who else by a raise of hand might be on a PC that we can also work to get installed and controlling? The process with KUKA-CRC, when I'm working with people around the world, is actually the first time I've also worked with people on other streaming platforms, is that I make sure to ask that the robot path is simulated for me to inspect before you send it. Since it's your first time on the robot and we want to be very gentle with Optimus, our robot here, we want to make sure that the path that you're about to send is been inspected and approved. Now, normally, if you got more advanced, we would certainly oversee the robot, but give you more autonomy to send robot commands without, a deep dive into each and every little plane that you're sending. But on a day one, certainly, we want to work closely together with you. So maybe I'll continue a little bit with my tutorial, and then you can tell me if you, in the chat, if you have problems installing the software. Keep in mind, make sure you unblock. Make sure you've taken out any other version of KUKA-CRC that you have on your computer, and then unpack it into your library's location. Hit me up if you have questions about that. You should be on the latest build of KUKA, of Rhino and Grasshopper, and a legal build at that. Okay, let me go back to sharing my screen.
So I remove also KUKA-CRC.
Yeah, the zip file that I sent includes PRC as well as CRC. So take your PRC out, save it somewhere for later, especially if you have a license, because the license that I've included is just for today's demo. And then we can you can delete CRC and bring back your existing software, which definitely I hope has a longer life.
Okay.
So let me talk a little bit about the Association and Robots in Architecture Research. The Association for Robots in Architecture is the academic side of robots in architecture. They provide accessible, very low-cost software for parametric robot control to the educational community. After 10 years, we've seen so many people come up through their design studies, through their prototyping, through their experimentation, people that have bought robots on eBay and set them up in their garage, people that have access to community spaces like the Autodesk Build space or shared spaces with robots, that we've seen a lot of startups come out of the educational community. So many so that we've built a whole commercial side of robots in architecture research. I have the honor of working with Dr. Sven Stum, our CEO, co-CEO and CTO, who's the lead developer of KUKA-CRC and has made it possible for me to collaborate all around the world with people like you and robots. Let me share my screen one more time. So far we've looked at sending commands through axis movements. We've looked at sending commands through planes, so inverse kinematics. But it's not really very interesting if you're just sending the robot to a fixed plane in space. So what I like to do is to keep this in my pocket, this little script here that I'll walk you through. So you've made a point in space and you want to move your robot to that point. but you don't want to be constricted to the normal orientation of that point. What we can do is deconstruct that point, set an amplitude, and move the origin of that point according to a specific axis of that specific plane. By combining that origin of that plane and that move point into a line, we can create an axis that then we can rotate that plane around. And by daisy chaining this little script 3 times, we can create a plane that has control very precisely around the X, Y, and Z of that local plane. So let's no longer look at just the basic X, Y, but let's look at the rotated plane. You can see that if we just send this plane movement to the robot by swapping out this command. So this is our merged commands where we have axis movement, linear movement, then axis movement. Let's just focus on this one movement of a limb motion. And we put our slider to 1. We know that since we turned on halt after last program position, it's moving to that specific location. And what you can see is now that we've deconstructed this plane and rotated around the 3 individual axes of that plane, we have precise control over where in space XYZ the robot is moving, in this case through Rhino interface. Let me just do one thing, which is turn off these grids. Always drives me crazy. But we have control over the orientation of the plane. So let's set this to 0, to 0, and to 0. So this is that basic XY plane. Let's also turn off our live preview of the robot. This is our basic XY plane. And what we can do is by rotating it around the X of that plane, you can see that we're able to change just that 6 axis. We can change more axis because inverse kinematics really doesn't need us to know the specific values of each individual axis. It just cares where are we putting the TCP of the robot, and it'll figure out through an inverse kinematic solver what to do with all these individual joints. You can see that it's moving the TCP of the robot, which is this axis right here of red and blue and green, and it's matching it with the axis of the plane. We're teaching the robot to move through planes axis by axis with regards to the TCP. And so now that we have control over where in space we're moving the robot to and the orientation, we could also push this command. So let's send it back through its axis movement. So we're going to say first move in this axis, then move to this lin command, and then do another axis movement. And let's have a look at what that looks like with the robot. So again, we can dial in our axis movement, making that maybe a little bit farther away from our lin motion. We can simulate this, making sure that there's no place in our simulation where the robot turns red. Looks pretty good to me. We can check that the simulation is good here because this would turn red. We could also go to our analysis and start to see a little bit more interesting of a robot program developing. Not too crazy yet, but we're getting there. Hit apply and exit. And then we can take this, turn on our live preview. Let me slow the robot down a little bit in my override commands. And we could send that along its path. You can see there's that axis movement. There's that lin movement. Now it goes back to that axis movement, and that's where we leave it. Now I could send it home through my local override. Again, a little more interesting in terms of complexity, but one movement in space, I mean, who's doing that? We want to build this up to much more complex movement. What we can then start to do is create planes in other interesting ways. Like say we have a curve that we want to trace along, and this could be the normal of a surface that we want to trace, or 3D print on, or paint on, or cut with a chainsaw on a robot, or plasma cut, or weld, or a million other things. We can make a series of numbers. We can make a per frame component, and we can take these frames from this curve and use this to generate planes for the robot. Now, what I've done here is taken all these 3 daisy chains of rotations and cluster them into just one little component that I keep in my pocket almost all the time because I'm always rotating planes. You can see that inside here is just what we walked through a second ago. Because I want to make sure that the planes of the robot, even though they're orienting normal to the planes of the curves, are going to be as I want them in terms of PCP orientation for the robot. So now we've gone from making an axis movement, which is forward kinematics, making a single plane motion, which is inverse kinematics. Somebody's not muted. Is it muted?
No, it's done. It's done.
No worries. And then we're making multiple planes by taking a curve and making perpendicular frames from those curves. So we can go from here into this Lin motion and take a look at what this looks like. Let's turn on some of these planes so that we can have a look at them. I'm also setting the interpolation to velocity based. And I'll explain what that does in a little bit, but let's send this command. So again, what we do is we're going to simulate this slider, make sure that it looks good. So there's that axis movement, and there's that series of motions and back to that axis movement. Let's do one thing maybe and take this a little bit further back. Good. Let's have a look at that. So I'm still booked. I don't have to keep booking it, but I could send this to true. And the robot jumps into motion. There's that axis movement. Let me move the robot a little faster. Moving to the start. Now it's tracing these planes as we intended. We could start to build up really interesting movements, not just through space in terms of X, Y, Z, but through orientation in terms of A, B, C. Now I'll send the robot home. This gets even more interesting if you start to combine it with apps like Fologram. So I have another demo that we can do where you can use your phone to record these points and move a robot through space. At our last workshop with our partners, Dagmar Reinhardt in Australia, they were using HoloLens to actually move planes in augmented reality from Australia and push commands directly to our robot. It gets really interesting. You can imagine taking this type of approach for generation of robot paths. So I'd love to go back to you guys out there in the world and try to get one of you pushing commands to the robot. So let's see, has anybody gotten it installed? If not, I'd love to share your screen and work with you to get it installed and to have you move the robot. Who's feeling lucky? A shy bunch.
We have one, we have Louis. Yeah, Louis has installed. So Luigi, you want to share your screen?
Yeah, Louis, let's share your screen and then I'll walk you through it. From Miami to Germany. This would be quite nice. Let me release the robot from my booking. Great. So what you need, Louis, is to have, you have to first off, let me turn on annotations. Go ahead and split your screen so that I can see Rhino and Grasshopper at the same time. Awesome. And generally, I'd maximize perspective mode. What you need to do is also connect this. So do me a favor, for username and password, I want you to put in, I'm going to send you something.
Okay.
Let's see. First off, it should be, maybe hide this so that people don't see all your email. Just try Luigi. Hold on, let me send you the password that I made for you. For username and password, you can try that. Yeah, I'll go ahead and show you the files again. Give me 1 second.
Okay. I put it here. I paste it here.
Mm-hmm.
Okay.
Great. And then what I want you to do is put a Boolean toggle right here.
Oh, what, sorry? Toggle?
Connect that Boolean toggle to the run WSS. I see you already have it there. Great. Now zoom out a tiny little bit and connect that panel to status and then trigger it to true. Okay. Interesting. One more time to false and then true again.
I think it's hang. It's not letting me do anything.
I think it would have been better to start with them.
Oh, there it is.
Perfect. Connected and login successful. That's what I like to see. Awesome. We're cooking with gas, as they say. Okay, now let's just send an axis movement. So you can see here, this is the part of the parametric program that's controlling the axis. So by playing around with these axis values, you can really start to see which axis is which on the robot. Now, please do me a couple of favors. Don't crash the robot into the floor. Don't crash the robot into itself. Try not to crash the robot into me. All these things would be greatly appreciated. Of course, I have local control, so I'm keeping a close eye on this robotic process. So that looks like a good axis movement. Let's go ahead and connect this axis movement specifically to robot. That looks good. So you're going to the robot. Okay. Now you see the simulation slider, which is in blue. Go ahead and DJ that. That looks like it's not going to hurt anything or anyone or break my heart. So let's strange that you're live robots. Right click. Let's see if you right click on this and maybe click this to false and then true again. Let's see why your live preview is not working. What does it say here on this little bubble?
Which bubble, sorry?
This little error bubble here. Okay, well, let's not worry about that for now. Let's first send a command and then we can worry about that later. So go to the book robot, down, down, down. So go ahead and book the robot. Okay, you're confirmed and go ahead and send it. Toggle it to false and then true again. No, not the other one. All right, let me toggle book robot one more time to true and false and then true. Yeah, and then toggle that the send to robot. I see you're booked, but nothing coming through. Go back to the show me the. Yeah, it's just connected and logging. Let me see your the address that you're sending it to. Double click on the address for me. Let me make sure that you've got that correct in there. Do me a favor, restart your Rhino and Grasshopper and just open up with a blank canvas. And let's go through setting it up from scratch. I think this is a better approach to it to give people an idea of the workflow. Maybe stop sharing your screen for 1 second as well. I think normally it's a better idea to build it up from scratch. People.
Oh, it says I have an update from Rhino. Could that be?
Let's try it without. Good. So I want to walk you through setting up the file from scratch so that when people get online a really good feel for it. So first, I want you to go to KUKA-CRC.
Let me hide this. I forgot where to hide the Zoom thing.
Sure.
Oh my God.
And in the chat, please let me know if other people have it installed or if are trying to follow along in terms of moving the robot as well. Okay, so first you're going to go to KUKA-CRC. You're going to bring down this lock component. I want you to right here put a Boolean toggle. And we're going to leave that to false for now and connect that to run WSS. Then I want you to put a panel right here. And in there, you're going to put that same username, which is lowercase df 00001. Good. And then click on this set login. You see here where it says set login?
Yeah. Oh, you cannot see the little screen. It's
yeah. Go ahead and copy that.
And copy.
And that would be what you're going to copy is this.
Sorry, copy from the chat. Oh yeah.
Sure, you can copy it from the chat.
And here. Okay. You can see the pop-up screen.
No, I can't, but it's okay. You can close that pop-up screen. It was more just to get the server address.
Okay.
KUKA-CRC works by connecting to an online server where you can get authenticated for credentials. Once these credentials are authenticated, we allow you to pass through the online server to our local server. So we need to make sure that this is the right address. So go ahead and copy, put that in a panel down here, the address that we put, this server.ip. Okay, and now connect this to address. And then let's put another panel over here and see if that connects successfully. Awesome. And now let's trigger this to true. One more time.
It's hanging for a bit, I think.
Okay, great. Now what I want you to do is go up here to robot operation and let's make a limb movement. Awesome. So we need to make a panel here, which tells us which robot we want to connect to. And in this case, we're going to make a panel that says Optimus. Let me put that in the chat. Now we want to connect that to device. And then we want to make 6 number sliders. I normally go -180 ... 180.
Oh.
That looks good. I would set that to -180 though before you copy and paste it.
Oh yeah. I didn't.
Awesome. And then make a merge component here that brings these together. I think that's one too many, actually. We've got 7 of them. Is that 1, 2, 3, 4, 5? No, that's right. We're good. Good. Now, what we want to do is we want to push this. We want to set up the robot to simulate this. So for that, we're going to go into, 1 second to push the annotation around. We want to pull down a translator. You see over here, there's the translator one. Note to the right. Sorry, I got my annotation a little wrong. Yeah, let's see that one. Make sure that's the right one.
KUKA-CRC?
We want to go from the one on the bottom. That's the PRC translator. It's this one here, this PRC translator. Awesome. Great. You can, okay, yeah, that's the same one. Good. So now we need to set up the robot. In order to do this, we're going to go to KUKA-CRC. We're going to pull down the Quantec KR90, KR2700, R2700. So go to your, go to virtual robot.
Yeah. Oh, is it this one or no?
Show me the drop-down menu.
Oh, okay, sorry.
And it's this one over here, the KR, give me one second. It's the KR90 to KR270, R2700. It's on the left under Quantec, KR90, yeah, that one. Perfect. Great. We also want to pull down a KUKA-CRC core component. And we're going to put that one into the robot. And I want you to do me a favor. Go to KUKA-CRC settings. I want you to go to advanced. I want you to turn this to as start under initial posture. My annotation seems to be a bit lagging. You see under start end position, initial posture.
Yeah.
Set that to as start.
What do I put at start, sorry?
You see initial posture.
Yes.
I don't know why my annotation's lagging. Let me try one more thing. Hold on. You see initial posture. You see
in here in KUKA-CRC.
no, in this, you're in the right window under there. You see initial posture right there up.
Okay, yes.
Yeah, set the to as start. I'm not sure why my annotation stopped working. Is that working? Then I want you to, down there, you see Alt after last program position, click that. And I want you to enter these values for the start and end position. For A1, it's going to be 0. Then minus 110. Then 90. Then 0. Then 90. And then 0. And then you're going to hit apply. And then exit. Awesome. I want you to do me the favor of bringing down the custom tool, which is under virtual tool, custom tool in KUKA-CRC. That one in the upper left-hand corner. And I want you to set this tool as the following values. Under X, if you click on set tool, see here, set tool. You have it open.
Yeah.
Sorry, I didn't see it. Or no, I guess I can't see it. For X,
let me share the screen so you can see it.
Sure.
Maybe that way we can see it. Share screen.
Okay, perfect. For X is 0.805. For Y is 1.237. And for Z is 203.191. 203.191. 203.191. Great, hit confirm.
What tool number?
That doesn't matter. Hit confirm, and now you're going to put that into the tool. Now we want to, we're going to connect the robot to the robot of the translator, and actually the commands to the KUKA-CRC commands. No, you see this one?
Yeah.
Hold on, let me clear my screen. So the commands that come out of your axis movement goes to the commands of the translator, like
Oh,
this.
like one of the translator.
And then the robot goes into the KUKA-CRC robot. No, hold on, let me show you. So from the robot, you go into the KUKA-CRC robot.
So
Yeah.
So this one goes this way.
No, into this one. Perfect. And this is what we're going to push into the KUKA-CRC commands. Awesome. So now let's look at your robot, because what the KUKA-CRC is telling you is that you're crashing the robot, essentially, I believe. So let's have a look. There's one other thing we need, which is our simulation slider. So right here, I want you to double click and type 0.9999999, as many nines as you want. That's good. Maybe and put that in your simulation slider. Awesome. Now what you can see is that your robot it's lying down. It's not so happy. There are some software limits that are programmed into KUKA-CRC that we want to avoid. So go ahead and play with the slider, play with these axis values to get a place where the robot's not lying down so much.
Oh, I see, yes.
Awesome. Now we want to connect this to KUKA-CRC. So you've logged in and connected. First off, save this file in case you crash your computer. Thank you for being my test subject here. That's much appreciated. I think it's a better plan. I always go back and forth between, do I start with an example file and confuse people from the start, or do I build it up from scratch and maybe we don't get as far as fast? I think today is a good compromise. I hope it works. So now what we want to do is connect to be able to book and send to the robot. So I want you to go back here to KUKA-CRC, and we're going to set up our book and send to robot by going to the core component of KUKA-CRC. Let me just check that. That's the one with the little cloud up here.
Yeah.
Right. Yeah, we want to put a Boolean toggle right here. I'd like to group that and name it as set, get booking or set booking. Maybe just group it, hit Control-G. No, delete that. We just want to group this and label it so that we know what's what. So hit Control-G.
Control-G, just with this one?
Just with that one. Yeah, and then you can label it. This is book robot. Great. Now let's copy and paste that and change that to send to robot with the group as well, or just group it again.
Oh,
Yeah, you could just kind of grab all of it and copy and paste it.
I think
if you go from the bottom left to the top right, and kind of like zoom, scroll over the selection, or you could just make a new one. Type Boolean toggle again. It's not that complicated that we need to worry about it. And let's group that one and say send to robot. Awesome. So this is going to be send program. And now what we want to do is, if you scroll a little bit to the left, what I want you to do is double click right here and make a data component. Just data. And we're going to group this one and label this one to robot.
this one, the data?
Yeah, just group it and label it to robot. This is going to be our pipeline to send commands through. So what I want you to do is take from this axis value into here.
From this one to this one, like that?
Mhm. And then we're going to replace this into the commands of KUKA-CRC. So this is pushing to our translator. And we're also going to place this into the KUKA-CRC commands. So we're sending PRC commands. And now do me a favor, make two panels, one here and one here.
In this place.
Mhm. And what I want to do is just briefly show the difference between KUKA-CRC and KUKA-PRC commands. So you can push into from here into here. You could look at one which is being translated and one directly coming from this. And what you see is that there's a pretty big difference between the level of complexity of PRC commands versus CRC commands. PRC commands are essentially G code for the robot. They're giving very specific access values, whereas KUKA-CRC commands have unique data identification, and they're formatted in a JSON string that are ready to send through the cloud from you in Miami, in Dubai, in Hawaii, in Tokyo, in Mexico, wherever you are, through the cloud in a low latency type of data structure, JSON strings, and then unpack it here on our local end. Now, because we're sending these commands with sync flags, you can see it says device, optimist, sync, false, and then metadata. All this information allows us to stream these commands that you're sending from around the world to the different devices that we have here in the robot hall and synchronize them so that the robot could move until it hits a sync flag and then dispatch a new command to a completely disconnected device. So through this distributed network globally, you around the world, to this distributed network locally, CRC is able to bring IoT Industry 4.0 ideas to robotic programming. For me, this is amazing because all of a sudden I could have a welder on one robot, and instead of connecting it to the IO of the robot, it's just getting an MQTT-based JSON string. So I could take that robot and put the welder on a different robot in 10 minutes, rather than calling up my electrical engineer and saying, I need a new CAN bus system built in hardware. So my robot can now go up to any of the IoT-enabled tools that exist in the robot hall, of which we've had 20 or 30 made by our students, and interact with these devices, whether it's a gripper, a linear axis, a plasma cutter, a sensor, a cooling device, a light, a button, all sorts of things can be IoT-enabled. Okay, so this is just to point out some of the difference, but that's less interesting than actually sending this command. So let's see the simulation one more time by moving that slider. Great, go ahead and book the robot by clicking the book commands to true. Great, I've got your booking, and now send the send to robot to true. Let me see your login component. It's strange that it doesn't send for you. You're connected and logged in.
Could it be a firewall on my side or something?
It could be. Do you have some firewall settings that you can disable?
Let me check.
Maybe you turn off your screen sharing for this. Let me
Yeah.
jump to some other people. I'd love to get a couple other people online as well. We followed the process. I think it's something with your firewall that's connecting because I'm getting your booking, and I'm. Let me see one more. Let me control yours. Can I control your You're
Yes.
controlling my robot. Can I control yours for a second? Let's see. So you've got the device is Optimus. That's correct. You're sending to. Yeah, but your booking is. Let me restart my the side from my side. Hold on 1 second. One second. Let me restart the server from my side.
And just to confirm, I think the Windows firewall is off.
Oh, very, very strange. Can you do me a favor? Let's just. Do me a favor, restart your Rhino and Grasshopper and maybe push that update to it. And let me pivot to somebody else and let's see who else has it, because I'm definitely getting the booking on my end. And it seems that it's not sending it from your end, even though it's, it's logging in successfully. So save this and restart your Rhino and Grasshopper, and let me jump to somebody else
Yes,
that maybe has it open.
will do.
Good. Is there somebody else that's got the plugin installed or would like to have help getting it installed?
Yeah, I think it'll be good if few others can volunteer, and it'll be good even if you don't have it installed. I think it'll be good to just share your screen and we can walk you through the process.
Mm-hmm. Don't be shy.
Yeah. I wonder if Ali or I know Leandra said she has a Mac, but if Ali, you were able to install or any success with that? Okay, yes, Mac too.
Let me get one more thing together that I can show from my side.
Yeah, maybe that would be a good idea. But if anyone wants to volunteer, yeah, that will be good. Even if you don't have the plugin installed, but you have it downloaded, it'll be good to take advantage of the fact that Ethan is around and you can ask him questions and even move the robot live.
Yeah. I'm used to a much less shy audience. BJ, Alawia, Andres, Ubudu, you guys have a PC that you can jump on? Mikta?
No, sorry, I just joined.
Do you have Rhino and Grasshopper on a PC?
Yeah, but I just joined the Zoom, so.
Perfect. If you're brave enough, I'll walk you through it.
Yeah, and I can drop you the download link. You must have not got the link from our chat.
Yes,
Start it again.
perfect.
Yeah. That's the link, and this should have, the link should have all the files. And I'll just post the message also from chat.
The nature of robotics is very, it's hard to imagine that you as an architect or an engineer or a creative designer really could work with robotics sometimes, because Normally, the traditional way of working with robotics is that a manufacturing company would bring in an integrator. The integrator would teach a robot one specific motion, for instance, picking something up and putting it to the next machine, and then they would run that motion again and again and again. I had an internship at a facade manufacturing company, and they had taught a KUKA robot to test doorknobs 1,000 times a day. The door was opening, there's nobody there, the robot closes the door. Saddest robot I ever saw. I said, you should put a picture of another robot on the other side. They said, that's crazy. This robot doesn't have feelings. I was like, it does. The robots have feelings. A better way for me to work with robots is to be able to mass customize robotic production. And KUKA-CRC allows us to do that. It does take some spaghettiing to get it up and running and parametrically controlled. But with the ability to push planes to the robots, we could start to mass customize what the robot's doing. So if we have a facade panel that needs something picked up and placed in 100 different ways, it's very easy to set up a parametric robot control program that would do that. And this gives you the ability to test and prototype your own processes for mass customization. And that's a real power, because if somebody says to you, well, we can't do that in our factory, you can say, look, I could simulate it on my computer at the earliest design stages. And I know that I've optimized my design for robotic fabrication. This is a powerful process, especially if you can, like so many of the people in our community, start building prototypes with that at an architectural scale or even at a larger scale. Go ahead and share my screen 1 second. You can see that the Association for Robots and Architecture is proud to make KUKA-CRC accessible to the creative community. You can check out the Vimeo page, which has a lot of interesting tutorials and information and examples of some of the really cool things that have been done with KUKA-CRC. You can also check out the Chair for Individualized Production and find out some of what we've got going on with our own research here as well. Stop that sharing. Luis, did you get your computer restarted? Not your computer, your Rhino Grasshopper?
Yes, it is restarted.
Can you share your screen with me one more time?
Yes.
I can say that this is par for the course with these workshops, that there's some time getting it installed and connected. And so I'm not phased. What we do in our courses at the Chair for Individualized Production is we're doing a lot of pick and place of rebar for robotic assembly and teaching our students how to digitally plan for mass customization and then optimize their tool paths for reachability and collision avoidance. We use tools like Octopus, Kerber, hologram, augmented reality, everything we can to bring as much information to the design process. We take into account robotic fabricability, reachability, collision, structural analysis, cost, and we teach them to build processes that can be tested on a small scale and then ideally pushed on a larger scale. Okay, so let's launch the CRC test and see if that helps us at all. Okay, so set that Boolean toggle to true. Now try to book the robot. Okay, I get that booking. Now hit send.
Oh, now it changed to true.
Set send program to true. There you go.
Okay, nice.
Awesome. Beautiful. Very cool. Okay, let's do a couple more things now. Let's keep going with you. And while this other very brave fellow gets his Rhino up and running and downloads this plugin. So what I want to do is the next thing is I want to create a point in Rhino, and we're going to make an inverse kinematic motion. So go ahead. I'm breathing a huge sigh of relief because I was worried that no one would connect, and that would be a shame. Now at least we have one motion. I could crack some champagne. Okay, so bring a point down. Good, you've done that. Bring a point down in the grasshopper environment. So you see up here. Yep. Go ahead and set that point. Great. Let's pick it up off the floor by turning on. Yep. Move it up off the floor a little bit. Hit escape. Yeah, there you go. Move it up, up, up. Great. What I want you to do is make an XY plane here in your grasshopper environment. Awesome. And then I want you to go to KUKA-CRC and pull down a Lin motion. Awesome. I want you to connect the device to the device. We're still going to use Optimus. And now the plane is the target. And we can double click here and type merge. And then we can bring the axis, whoops, moved around. We can bring the axis as our first motion, and then this Lin motion as our second motion. And now let's push this to to robot. Great. Now you can see that we get a little bit more complex. We can simulate that. That looks good to me. Let's go ahead and send that by setting the send robot back to false. You could stay booked. No, the booking has to stay true.
Sorry.
But you could stay booked. It's your party. And then set it to set the send robot to true. Awesome. Nicely done. Let's go ahead and try to set up one more thing, which is the display of the live robot. So let's go up here to KUKA core. I believe it's that one, display, yes. Bring that down. We want to, again, tell it that the same device, we're going to keep connecting to Optimus. We want to connect the custom tool. Actually, I think you don't have geometry for the tool. So what I want you to do is put a Boolean toggle here for setting this to true. So we want to show 3D. And then I want you to put a trigger below that. Double click here and type trigger. And we want to set that to 200 milliseconds by right clicking on this part. Go to interval, 200 milliseconds. And then, yeah, you kind of connect it. No, to the, yeah, to that one. Okay, now, let's see if you set that to true. Please keep in mind that this is a beta test of everything. So let's see. Awesome. So now I just sent the robot to home and you can see that live robot moving. So let's go ahead and make another command, simulate it, and send it again.
Okay, so do I make a new one or I just move the point?
You could just move that point. But at this point, the philosophy is clear. You could also make another point, make another, let's try that actually. Let's copy and paste all this good stuff and make another Lin motion. And we can look at the difference between a Lin motion perhaps and a point-to-point motion. This is always quite interesting. So copy and paste all that. Make a second point in the Rhino window. Sometimes you have to clear this point in order to set it again. Maybe you can just clear values and then set that one point. Great. And now let's add this to D3 in that merge. And now let's simulate it and rotate it. Maybe move this point a little bit farther away and a little bit up. Just to be safe. Yeah, that looks good to me. Okay, let's simulate it. And looks good. Let's go ahead and send it. It's pretty low latency considering from Miami,
Yeah.
under the Atlantic,
Oh yeah, that's fast.
across London, through the tube. Now you can see because we're moving in a Lin motion, it's going directly from plane A to plane B. Let's do one other thing. Let's change that second motion to a point-to-point motion and look at the difference. So you see here, there's a point-to-point motion. We want to use that as our target. And then Optimus again. Or what's even better is if you make a third point as well. So maybe copy all that good stuff. Now, point-to-point motions allow the robot greater freedom between plane A and plane B. So what you're going to see is that the robot doesn't move in a direct straight line. It's going to move kind of in an arc in a way that's most convenient for the robot kinematic system. That's good if you're hitting singularities. Singularity is a point where multiple axes of your robot are perfectly aligned, causing, let's say, kinematic confusion. That's not the technical term for it, but essentially you can get an infinite amount of paths through a point, and it's not, the inverse kinematic solver is not able to calculate it fast enough because there's so many options and you get stuck. So for instance, the most constant singularity that I'm bumping into in my life is where the wrist and the forearm of the robot are perfectly aligned. And you'll see then it kind of tries to go through it too fast and hit a stop point. And what you can see right now is that this limb motion is going in a straight line, and then the point-to-point motions will go in this arc. So there's a limb motion and there's a point-to-point motion. Now that first motion is point-to-point because it's the first motion in KUKA-CRC is always a point-to-point, even though it's limb. So interesting factoid, but this is the difference. So let's go ahead and send that program. There's that first axis motion. There's that first motion. There's a limb motion. You can kind of hear it. It goes through a little bit close to singularity. And then I understand it's not going to that point-to-point motion because we haven't set the status and turn properly. I gotta say, let's leave that for a different tutorial. The status and turn, I would have to, hold on, let me see. Display. Do me a favor. On this limb, point-to-point, status and turn is a more advanced subject, but I'm gonna tell you something right here to put under status. I want you to make a panel and put 110. And then make another panel underneath this and put 011, 011. Status in turn talks about the quadrants that the robot arm is located in, because point-to-point motions extract the previous status in turn from a motion. And if the status in turn is not correct, it might vary from the simulation that we're sending it. Let's try it one more time with this. Let me reset the robot and send it home. So if you put that one into status and the next one into turn, let's see if this solves this kinematic little kerfuffle here. Let me send that home. 1 second before you send it. Okay, let's try that. Send that one. There's our axis movement. Then 1. What do you think? Pretty cool?
Nice.
Yeah. So let's get rid of that point-to-point motion. We would have to set that a little bit differently. Let's do all limb motion. What I want to do is one more thing though, is I'd like to start taking one of these planes apart and extracting it into something that we can control more precisely. So follow along with me. I want you to double click and type deconstruct plane. Or maybe plane deconstruct. Maybe type plane deconstruct.
Oh.
There you go, that one. Great, now I want to put that XY plane into the plane. Let's rip that plane apart into its pieces. I want you to follow along. I'm going to double click here and say move. Double click and type amplitude. Double click and type 1, yes. So we want to move the origin according to a vector of x by an amplitude of 1, and that's our motion for movement. Awesome. Now we want to make a line. Double click here and type line. No, the line from 2 points.
With the origin and the vector.
The origin and the geometry that's been moved. And then you want to double click here and type rotate. Rotate. Yeah, that works out. So the geometry that we want to rotate is that original plane, but I want you to do one thing for me. Make a data component here so that we can make this easy to kind of cluster. And then put this plane into here and let's replace that plane. And then this plane is the one that the geometry that we're going to rotate. And this is our axis. I'm sorry, I think you got the wrong one there. Let me check my file. I think the one that you want is rotate around axis. Yeah, rotate axis is the one you want. Very cool. So that one goes to the axis. You have to right click on angle and type in and set it to degrees. I personally don't really use radians. You see degrees there. Hit that button that says above expression. Yeah, and then you can double click and type -180 ... 180. You send the robot home while we're doing this.
180.
And that could be your angle of rotation. And then what we want to do is, hold on one second while I reset the robot. What we want to do then is put another data component on the outside of this. And that is going to collect our geometry. Great. Now we want to take this whole party and group it and then copy and paste it 2 more times. Not the whole party, just what we just did from data to data. Including that first data one also.
Oh, okay.
And then switch out this data for that one. Whoops. This data for that.
Right.
And then we want to daisy chain this. So we want to go from one data component to the next. And then grab this again and copy and paste it 1 more time.
Yeah, for loop.
And then like this, boom, boom. And now what we want to do is we want to get in here and change the axes that we're amplitude moving to Y, and then the next one to Z.
Okay, so X, Y.
And then this last one, Z. And now let's, can we show this plane? Maybe your planes are very small. We could say display. Oh, no, I'm sorry, display up here in the grasshopper. Go to preview plane size and maybe set that to 200.
Oh.
See down, 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 preview plane size. Yeah, set that to like 200. There we go. Now keep in mind that the plane of the TCP, you see that red line that comes out of the TCP, it's red, blue, and green. That's going to match the red and green of the TCP to the red and green of that plane. So by changing these values, we can get a rotated plane that allows us to control XYZ from Rhino and then ABC from Grasshopper. So this can be a plane that we can put now into our target of CRC and change some of these values. So we're not just moving kind of in the XY orientation, but we're moving in customized orientation. That makes sense. So our file's getting a little messy. Maybe we clean up a little bit, but essentially we want to take this plane and replace the plane of our target of XY in here, this one. Oh, this one. You see our target? There you go. Perfect. And now let's move the robot to the end of its simulation. Getting a little messy. We'll go through and do some cleanup. Okay, and now change those values for 180 to, not all the ones, the values that we just created for the X, Y, and Z rotation, like these values here.
Well, that's
these ones.
That's the X, yeah.
And now you can see you have very precise control, not just over where the robot's going, X, Y, Z, but the orientation in ABC. Because you really have precise control over the planes. So get it set up so it's quite nice. Like maybe right now, change maybe in one other, change this one a little bit. All right, let's try sending that. Run the simulation. Do we still have it set up to first simulate it?
Oh yeah, sorry.
Do we have that set up still point to point, or no? That's still Lin, yeah. Good. Awesome. That looks good to me. Let's go ahead and send that. You can see that sometimes, hopefully all the time, the robot does what we tell it to. Let's do one thing that's a little bit more complex, which is let's make an interpolated curve in the Rhino environment. Please feel free. I'm continuing with Louis because nobody else has jumped up, but I would love it if somebody else tries to push the robot around. Not push it around, program it, let's call it. Push around, that sounds a little bullying. Push commands to the robot, that's what I mean. Good, and maybe make that a little bit more three-dimensional somehow. I usually use the gumball just to make sure that it's in one axis and not doing crazy motions.
Also,
good, that looks good. That's okay.
Oh yeah?
Yeah, sure, let's find out. That's the point. The point is to use Rhino and Grasshopper to discover if a design is fabricable. So we get this early design decision feedback. Rather than having to go to a specialist fabricator and saying, can I build this with a robot? We can say to people that, I know you can build it. I've tested it with the robot, with the setup. Dubu, I'm gonna share that definitely with you. I would love it to get other people on it.
Yeah, I think we do have email IDs, or you can share it here in the chat as well.
Mm-hmm.
Just the graphical file. Yeah.
It's on the same Cybo.
Okay, great.
I feel like if you want to try it though, share your screen and we'll walk you through it step by step.
Yeah, I think that's a better idea.
This is much better.
Mm-hmm.
Let's do a couple of things here though for you. I want you to take all this good stuff here, Louis, and like move it over to the right. It's nice to make a mess, and then every once in a while you got to clean up the mess so that people later on in the future can follow where all this spaghetti goes. Oh, much better. Now I don't feel so crazy. And then one other thing that we can do, Louis, is go back to all this good stuff that we built here. Let's cluster this. So from this data component all the way to this one, I want to cluster it, but leave out these, leave out this, this, and this. Leave out the controls from the cluster. I should really make this little part. I'm sure there's an easier way to do this. I rely on this tried and true trick of deconstructing the plane. So just right click and say cluster. Ah, even better. Perfect. Great. Now we have a nice little tight component that we can use again and again. Good. So what I want to do is let's bring this curve into the Grasshopper environment. What I want to do is make perpendicular frames on that curve. So double click next to it and type perp frame.
Type what, sorry?
Perp frame, P-E-R-P.
P-E-R-P.
Yeah, the second one, perp frame. What this is asking for is a curve and a parameter. So for the parameters, I want to make a series of numbers. So double click and type series. And the series needs to go from 0 to 1 because we're going to reparameterize this curve. Reparameterization takes a series of numbers or a curve or a surface and remaps it so that the beginning is always 0 and the end is always 1. So in order to do that, we're going to make a series of numbers. So right here, type 0.1. We want to make a series of numbers that go from 0 to 1. No, sorry, that needs to go into step, not into start. And this is going to go into your parameters. So from 0.1, 0.2, 0.3. But now what we need to do is we need to reparameterize the curve, that the curve also goes, so right click on curve. Right click on this curve. You see, no, on the, apologies, on the curve of the perp frame component. Right click there and then say reparameterize. What this is going to make is that the curve is always going from 0 to 1. So 0 is always the beginning and 1's always the end. In this case, we're going to 0.9, but nevertheless. Then what we want to do is let's copy and paste this cluster. And we can put these frames into the geometry and into the plane. I think we didn't get that so efficient. Zoom in a little bit for me. And into the plane as well. I guess we could have made that cluster a little bit better where we only had one input, but perfect. Now hide this stuff.
Hide it.
Yeah, just turn the preview off of the perp frame.
Okay.
And just right click and say preview off. Great. And what we want to do is flip it so that the red is pointing down. You see that red axis of the plane?
Yes.
We want that to be pointing down. So let's rotate these. Let's set all these to 0 and then figure out how we could rotate this plane around its own axes so that we're still staying normal to the curve, but we're in the orientation of the tool center point that we want. So actually, let's see if we set it all to 0. So it was close. I think it's that last angle that we need to rotate a little bit. You can tweak it. And you see how now you're rotating around the path? Okay, well, let's take this plane and put it into the robot Lin program and see which one is most reachable by the robot, because there are going to be some that's not reachable. So double click here and type and bring down the CRC Lin component. Rather, probably go up here to the Lin one. I think that's the axis. I apologize, I annotated wrongly.
Oh.
So we want to, again, connect this to Optimus. We always have to keep telling what robot we're going to connect to. I'm sending the robot home, so don't get scared. That's not you. And this is going to be our target. Now, what I want you to do is also flatten this coming out of here. And then let's bring that into our stack of commands that we're designing in this very strange robotic process that we're developing for demonstration. Or better yet, zoom out. Let's just send only these commands. So push this into to robot. Let's just focus on this new program of following this curve. Okay, now let's simulate that with the robot. Before you send it, we always simulate. Let me get rid of this. All right. Let's see again. And I want you to do, all right, that looks good. Go ahead and let's send that. Slowed it down a little bit there, got a little spicy on us. Now what you see is that the robot is starting and stopping at each plane. Also, you see that you might be getting very close to my welder, so I might stop you a little bit.
Okay.
But that's okay. What's happening there is that we haven't set any interpolation value on the robot. So the robot is ramping slowly up to full speed and then ramping slowly down to halt at every plane for a small moment until it plans the next path. This leads to kind of this start and stop motion, but it's highly accurate. Please keep an eye on it. What we can do though is use interpolation to give up a little bit of accuracy. So to allow the robot some deviation from the very specific point that we want it to go to in hopes of or achieving a more consistent speed. So I want you to go to that Lin motion that we just created, and we're going to set some interpolation value in there.
Okay.
So you see this A type. If you hover over A type, you can see that there's distance-based interpolation, orientation-based interpolation, and velocity-based interpolation. These are different types that are worth going into in a longer session. Let's just for now set it to velocity-based. Distance-based interpolation is going to say that, say you set it to 10 mm, and you have 3 planes to go to. From plane 1 to plane 2 to plane 3, with no interpolation, it's going to start slow, get to full speed, stop, ramp down, and stop. And the same thing to this next point. With distance-based interpolation, it's going to say at 10 millimeters to plane 2, start moving to plane 3. So it's never going to quite hit plane 2. In order to keep its speed consistent, it's going to work its way with a little bit deviation from the specific design path to the next point. So I've been studying for my PhD a lot about how the balance between deviation and interpolation and consistency of speed interacts with specific processes. So go ahead and send that, and let's take a look at the different paths.
Is it possible to stop the robot remotely?
No, we don't give you the override control. But I can say that we're interested in these ideas because as a beta tester, we definitely want to know what would be interesting. Ideally, we don't really have live override control remotely because I want to be able to see myself here with the real robot and have local override control.
Yeah.
Awesome. Very cool. We can do one other thing here. Let's try this. Is if we so let's copy and paste this and try to stack another motion to it. I would like you to get a couple of motions more ready for a more complicated path. And then let me jump to the other users and see if anybody else wants to try to push the robot. I applaud you for helping me show that this really works.
Okay.
I promise it does. Let's jump to some other people and see if anyone else has followed along. I asked Luis that you don't send to the robot without me. I'm actually going to remove your booking.
Okay.
But please let me know if you're going to push the robot.
I'll remove it too in here. I'll turn it off just in case.
Perfect.
Thank you.
What's interesting is that other people, if you're connected to KUKA-CRC, should still see what Luis is doing with your live robot. So we've played a reverse type of Jenga game around the world where people have been picking up and placing a piece of rebar. I've welded it in place. And then we have a wait for user commands that you can put, which allows me as a local operator to know that the robot's not going to move until I hit a button, an IoT enabled button on my hip, so I can get into the area, weld something. And through this history command, we can push this collaboration, this movement where Luis placed this piece of rebar to other users, and then you could build off of that. that generally takes about a 2-day session for us to get up to that level of robot control. But it's really interesting to build not just distributed collaboration where you from around the world can connect to robots around the world, but where you and other users could also start collaborating by sharing metadata about robotic movement. You can imagine that if you had a remote robotic production facility, you might be able to keep tabs on the production process and see which element of the mass customized, sequence of events is happening, or which part the robot cell is working on, or when a robot's available, or even better, to test if it works with that size of robot and say, okay, 80% of my facade production needs to go to this factory that has a Titan, but the rest I can do in a more local factory that has a smaller Optimus, for instance, and start distributing these commands in collaboration. Let me one more thing. So what this provides is a really interesting ability to control robots. I love the work of Madeline, who works with Madeline Gannon, who works with her robot Mimus. By now she's working with other robots, and she's teaching robots to work with people in more intuitive ways. She's got the ability for robots to see what's happening with markers or with her hand motions or the environment around it and react accordingly. My favorite scene of any movie is Iron Man, where he says to the robot, hey, dummy, sweep that up. And the robot knows what he's talking about. If you think about the next generation of roboticists, we're going to be working with robots in much more intuitive ways. Parametric robot control is one of them. Cloud remote control is another. We could do something similar to what we just did with making planes through a curve, but making planes with our phone using an app like Hologram to find out where the planes are on the phone in space. This gets really interesting. Carl Stingline recently posted a great example of ChatGPT being used to generate robotic programs. And so I think the future is really open and accessible. And part of CRC's goal is to bring robots into online collaborations. And my goal is that, we can all be sharing fabrication facilities around the world in a safe Internet of Things enabled fashion. I think it really opens up a lot of possibilities, both in times of pandemics, which I hope we never go through again, and we can't travel and we're locked in our rooms. But also, I mean, let's be honest, from a carbon footprint point of view, it's not that easy to get on a plane and travel around the world to a workshop. It's nice to be able to wake up and log in to a robot in Chile somewhere and do some woodworking, and then log in Michigan to a robot person 3D printing of concrete, and then log into another facility here in Aachen for some metal manufacturing with me and Robots and Architecture Research and the Chair of Individualized Production. I think that the more access we have to become digital craftsmen with the robots, the more we can push the limits of our design to fabrication processes, and the greater connectivity that we have as a community. I think the stronger we can grow in building these relationships, these collaborations, and these ideas. So part of my work is to bring the IoT-enabled aspect of sensor data into adaptive processes. And this is something that's not yet part of CRC, but part of Robots and Architecture and the Chair of Individualized Production Research and part of my PhD, so that we can say, for instance, if the robot's not picked up a piece of metal, okay, trigger an IoT-enabled camera to reposition the pickup plane and then send that command again. Because actually in construction and especially steelwork, precision is much wider tolerances for construction and fabrication than robotics can adapt to. Robotics are great at dirty, dull, repetitive, dangerous tasks, but they're not that great at adapting to changes in design environments like humans are. Humans say, hey, it's in the wrong spot, I'll just change where I'm picking it up. But a robot doesn't know. And we're working now through cloud remote control to bring eyes and ears and adaptivity through sensor integration to the robotic process in a more state-like way. Really interesting. I'd love to try and get some feedback from the community here. I'm glad that we got one demo. It started bumpy, and then kind of we hit our stride. So if you're watching this, I hope you made it to this part of it.
Yeah, it's part of the process. But no, Ethan, I have to agree with you. There are just so many directions now, things that have opened up just with the introduction of robotics. in architecture, and I cannot even begin to say the way everybody is using robotics at the moment and what KUKA-CRC will bring into the equation altogether. And I can't wait to get my hands on to the final version, and I hope we're able to see the final version very soon, available for everyone to work. But just on that note, I still want to urge anyone who would want to share their screen or ask any questions to Ethan.
Yeah, can I ask one question?
Mhm.
Please.
Yeah, maybe, but that's not related to the script. I'm wondering, do you also teach undergraduate student for this robotic parts?
Say
And
one
if
more
you
time.
do you also teach undergraduate students these robotic parts, and what level if you do so? Thank you.
Yeah, we definitely, I teach specifically at the RWTH Aachen. We teach architecture students. We have a master's in construction robotics that we're teaching. We're now working on releasing a massive open online course that's going to walk through in much, much greater detail KUKA-CRC to bring parametric robot control education to even people that are not registered as undergrad students. We teach workshops all around the world. I'm really excited to announce that KUKA, that the Robarch conference is coming back in full effect. We're going to make an announcement soon for 2024 and hosting that around the world. It's super exciting. I can't really say just yet. And there we'll have definitely really interesting workshops. There's a lot of tutorials online at the Individualized Production website, and on the Robots and Architecture forum, you can find examples certainly. One of the things that's great about Grasshopper and the association, and in general, the computational design community, is this crowdsourcing of knowledge. People like DigitalFUTURES, which is making knowledge accessible, and other organizations that are really working hard to bring these ideas out and make them accessible. We definitely don't want to keep these things secret. We want to see what people do with them. I think it's the younger generations that'll have ideas that change the world. I'm sure at some point there'll be robots on Mars that you can control remotely. I'm sure there'll be underwater robots that you are interested in finding renewable sources of energy with in the future, or medical robots. There's a whole field of aspects, deconstruction robots, all sorts of things that I think, ideas that we hope that we haven't even thought of yet, that we want to, that opening access inspires innovation, let's say. I'm a strong believer in that. And I think that by sharing these ideas and sharing these tools, we definitely want to see what people do with them. We like to push things to the limits. I mean, you're definitely not supposed to use MXA in this kind of fashion to connect from around the world, but it's possible. And the best thing you could have in life is a naivety to what's impossible, because then you can just do things. Like when I tried to build public art projects, I didn't know that it was impossible. Now I think, oh my God, what an impossible thing to do, to put a giant sculpture up on the wall from San Francisco to DC. But I didn't consider whether it was impossible then. And so if you're somewhere on the line of computational design and engineering, you think nobody's willing to build this, it's possible. You can prototype it and push, simulate it and execute it on a small scale yourself. One of my favorite teams in architecture is Elements Architect out of Seattle, and they did a really beautiful roof in Iowa. And they built a prototype in their backyard with a small CNC machine. And by the time the client saw it, they're like, I see that even though it's mass customized and individualized for function and performance and aesthetics, it's actually not any more expensive to build because the code is direct from design to manufacturing. And that's really powerful. A lot of whether ambitious ideas get made come down to the design consideration and the functional aspects of it and the cost. And fabrication is a huge cost in creating complex ideas. I think actually computation has grown to not be as sculptural, and that now we're more seeing people using computational engineering to make high performance buildings that don't look as crazy, but perform better sustainably, cost-wise, for just the user to inhabit. I love tools like Ladybug and Honeybee and Karamba and all these things that are looking at not just is the building crazy and can we build it and it's all double curve madness, but is it more solar efficient? Can we save money by having a customized shading screen? One of my favorite buildings is the Al Bahar Towers in Abu Dhabi, which has a dynamic mashrabiyah, which was led by one of my previous team leaders, Abdul Majid Karanu. And I love that this building was, from a DNA point of view, focused on performance. And of course, the aesthetics are interesting because of that. But what allowed it to get built, I think, was the positive impact it had on the function of the building. And I think robotics, it needs to be one of these early design decision assistance tools that if you say only late in the process, now I want to build it with robots, probably not going to be designed for such fabrication. But if it's like at the conceptual stage, made for robotic production, then I think there's a higher chance where you can say, look, this is designed to be built with robots. I know we can do it. I did it from Miami to Germany. That's a long answer to a short question, I think.
No, I know.
Awesome. Cool. Thanks.
Yeah, we definitely will be posting by summer, I hope, this massive open online course. And I'm getting this out to the world because we definitely are excited to get more and more people up to speed with KUKA-CRC. It's been out there a long time, but we're always interested in sharing this knowledge more and more.
Yeah. No, Ethan, again, thank you so much. I'm glad that Digital Futures was able to be instrumental in just getting the word out for you as well. I just have one question regarding if there are labs who would want to collaborate or reach out to you and see if some better version of KUKA-CRC is available for them to use or test out with you, where can they reach you? And even same for students as well, like after watching YouTube, if they want to reach out to you.
For sure. Let me share this screen one more time. Certainly, I love LinkedIn. I recommend hitting me up, Ethan Kerber, on LinkedIn. But also, I'm a huge fan of reaching out by email. You can hit me up at ethan@robotsinarchitecture.com. We just pulled down our website and are rebuilding it, but this is we will have that up shortly. This is a great place to reach out to me or to hit me up on LinkedIn. I'm always interested in seeing where people are going, even if robots is just a small part of your journey or just a side interest. I love the whole world of computational design and engineering and construction. I've got a lot of other interests also, kite surfing, sculpture, music, but I definitely, if you're interested in testing KUKA-CRC, reach out. We definitely are working to get this deployable. Our goal is by the next, we're working to get this deployable at other labs. And this is something we definitely don't want to have, as much as I've enjoyed throughout the pandemic, being kind of able to share our robots with the world. I also want to check out the robots that you have in your lab, certainly. So this is a good spot to reach out to me.
Yeah, sure. I think I'm sure you'll get a lot of questions, Ethan, because there are many of our students and audience who would be watching it later from our YouTube recordings. And for those who are here on Zoom, you already have some access to files. Please reach out to Ethan, or you can always reach out to Digital Futures at info@digitalfutures.world. And
I want to say one more thing. I will, the plugin that I gave you won't be accessible for people later on. I'm going to take down this link. It is something that we very carefully control who gets on the robot. So I've created these credentials for today, and I will disable them so that in the middle of the night, if I'm here working, I'm not in the middle of the night, during the workday, somebody's not jumping onto the robot and swinging it around. So we do focus. There's a huge level of security built on into this software. Certainly safety is our highest priority, and this is something we take very seriously. So please, if you're watching this in the future and you don't see the SIBO link that I've shared or the plugin yet available on KUKA Rhino or in your plugin manager, please reach out and we can talk about another chance. We're going to have more regular workshops for KUKA-CRC and look for more opportunities to build up this knowledge around the world, and definitely to get this this out there. Normally, we do have longer time together. This is a rather short session to pack a lot of knowledge into your head. I know I've taken workshops with Digital Futures and I turn around for a cup of coffee and there's like 10 more components on the screen. And I'm like, how did they code so fast? So please definitely watch this again and reach out to me if you want to discuss future workshops or future opportunities for integrating this. I think one thing that I have to give credit to Professor Beltrochen, to Johannes Brauman, to Sven Stum, is that they really have a big vision for modularity and extendability of design software. So what KUKA-CRC is built on is the core of KUKA-PRC, which is made to be used in ways that we wouldn't even imagine. And so if you have ideas, it's amazing for me to see when I come up with ideas for my PhD, how the infrastructure that's already established can be extended in a modular way. So this is really the power of good programming, is if you can build on top of things like Grasshopper and then PRC and then CRC and then your process for saving the world, I hope, because certainly there's a lot of work that we have to do. And I think what we do with robots, we're still at the very beginning of this journey, I would say, about bringing digitalization into architecture. And I think there's, it's amazing. It's like we're still at, I think, at foundational level of the impact that we can have on the world with these tools. So I very much thank you for sharing your time with me, for organizing this event. I hope that you out there in the world are inspired a little bit, or at least entertained a little bit. And nothing's easy, but it's all super fun to work on these challenging problems and opportunities.
I think, Ethan, of course, one thing that Digital Futures and Robots in Architecture and your initiative share is, of course, making knowledge accessible, and that's more important and critical at this moment. There is some message for you in the chat. If you can just check while I wind up the event by just announcing our upcoming sessions. Yeah.
Great.
So
thank you so much.
yeah, once again, thanks for your time, Ethan, and definitely thank you so much for the audience who have joined us on Zoom and those who will be watching on YouTube. We also have another session in about 1 hour, 30 minutes at 2 p.m. EST on prompt engineering, and in Midjourney, DALI, on AI. There are a series of lectures that are happening every Saturday. And tomorrow we have doctoral consortium sessions beginning on architecture and philosophy. Please do join us and check Instagram and our social media post for upcoming sessions. And looking forward to your responses, everyone. Okay, have a great weekend. Bye. Ethan. Thank you. Thank you.
Bye bye.
Thank you.
Yeah.
Thanks.
Mhm.